Alright, welcome to Lab 3. I am Raquelme. Let's jump into it. So for the introduction, the idea of the lab is to simply understand how electrical circuits work and how their charge can be measured using real circuit equipment, which is provided during our GPS labs. And then you have the purpose of the lab, and that's just to predict and notate circuit behavior using different things like resistors, batteries, meters, and capacitors. And so system versus surroundings, the system is the circuit, and surroundings just everything else. So the preview, after everything that was experimented, the node rule holds true, and so does the loop rule. So fundamental concepts, of course the node rule, it just relates to conservation of charge, and it's just the current flowing into a node must be equivalent to the current flowing out of it. That's the simple definition of it. You can see it on the top right. Then you have the loop rule, again relates to conservation of charge, but this one can be described as the sum around a loop of potential difference is always going to be 0, and then that's right in the middle. And then you have Ohm's law. That's just the current through a conductor between 2 points is proportional to the voltage across the given points. You just kind of see what that's talking about down in the bottom right. So the initial ammeter readings, this was basically the setup of during the lab. You had the 2 batteries, which then connected to the first ammeter. Then you had the 2 resistors and the second ammeter. And so the first ammeter, that one read 18.3, and then the second one read 18.7. So then what we did in the lab was get rid of one of the ammeters, the first one in our case, and then connect a voltmeter there. And so the reading of the ammeter went to 0. This is referring to the second ammeter. The first one was gone. And then the voltmeter, this was because the voltmeter has such a high resistance, it basically takes away all the voltage from the batteries. And so the voltmeter registered a total charge of 3 volts, but no other component was active within the system besides just the 2 batteries sending their voltage directly to the voltmeter. Then you have the voltage drop calculations. Basically the loop rule, all the voltage when you go around the loop will basically equal 0 at the end of it, the difference of the potential voltage. So you have delta V from AB, that was positive 3 as the 2 batteries increased the charge. Then you had delta V from C to D, that's the first resistor, minus 0.96. Then you had from point EF, that's negative 2.04 volts. Then you had the ammeter and the rest of the areas, which is 0 V for delta V. So you can see what that kind of just means in graph form. Again, the batteries from A to B, and then you have the 2 resistors from C to D and E to F. And then again, everything else just remains constant. So a question, when you attach the voltmeter, you alter the circuit, why doesn't the ammeter reading change? Well, it's due to the voltmeter having a very high resistance and only a tiny amount of current flows through it. So the ammeter wouldn't change. So the voltage drop calculations, that is the wrong title, but basically this relates to connecting the parallel ammeter, and so due to the lower resistance of the ammeter compared to the 100 resistor, the total resistance through the current lowers to only 47, since the current basically goes around the 100 volt resistor, and yeah, skips it basically. So the resistance calculations, you had 46.6 ohms for the first resistor, 97.7 ohms for the second resistor, and the wire was just 0.2 ohms, and the ammeter 0 ohms. And then the RC circuits, this was with the light bulb. So basically the time it took for the capacitor to charge was 74 seconds, the time it took for the discharge was 47 seconds, and this again we just simply attached the battery, the bulb, and the capacitor, and then let it charge up, disconnect the battery, and let the capacitor kind of drain away and send its energy, its voltage to the bulb. So potential errors, the primary potential error was just simply human error, not much else. And so what if you charge the capacitor with no resistor in the circuit? How quickly would our ideal model predict the capacitor to reach full charge? Would this prediction happen in real life? Explain. So if a capacitor was attempted to be charged with no resistor in the circuit, it would in theory charge almost automatically, as there's no resistance preventing the capacitor from receiving the charge. In practice, there's always a delay though, so the experimentation results will be a little different than the theoretical ones. And that's all. I appreciate it. Thank you.